inviting me to give a talk on this platform. Uh, so, okay. So this talk is based on our recent work with my student. I acknowledge his contribution for this work. So here we talk about inverses of non-bipartite unicyclic graphs. So in the literature, so far we can see so many works on inverses of bipartite graphs. So this is a small step towards the non-bipartite case. So this talk will give us some overview of that. So before we begin, we start with the definition of adjacency matrix of a graph. Most of us familiar with this, but okay, let's have the definition. Suppose we have a graph G of order n, whose vertices are say from 1 to 2n, then we know that the adjacency matrix is n by n matrix, where rows and columns are corresponding to these vertices, and the ijth entry is will be 1 if I and j are adjacent, otherwise it is 0. So for example, we consider this graph G, and its adjacency matrix is this. So whenever a matrix is in front of us, we usually see, first thing we will see whether it is singular or not. And we see that it is singular. Then we take another graph, slightly different, and we consider its adjacency matrix, and we see that this is non-singular. So now it is confirmed that there are graphs where adjacency matrices are singular, and there are graphs where adjacency matrices are non-singular. So in view of that, one can define whether a graph to be singular if its adjacency matrix is singular, otherwise it is called non-singular. This is what people define the singularity of a graph. And before we move, let us talk about some preliminary things. Now, what is a spanning linear subgraph? It is a subgraph, spanning subgraph, all of whose components are either edge or a cycle. And what is a perfect matching? A perfect matching is just a spanning linear subgraph, all of whose components are edges only. So for example, we take this graph, and this is a spanning linear subgraph where all of its components are edges. So one can say this is a perfect matching. And the edges, that means the components in this spanning linear subgraph, are nothing but matching edges. This is all we know of these things. So we have the graph Z, we have its adjacency matrix G. We have seen some graphs have adjacency matrix singular, some have non-singular. So singularity and non-singularity can be connected with the determinant also. So people thought of whether the determinant of the adjacency matrix of a graph can be described in terms of the graph itself. Then Harare and Sartre, they have came up with a solution to that question. They have independently found this formula for the determinant, okay, which tells us determinant of the adjacency matrix of the graph in terms of the graph structure. I think in the 1962 or something like that. They have independently found this. So that's why the theorem named, not I, people name this theorem after Harare answer. And because of this theorem, one can easily see that whenever a graph has unique perfect matching, then it is always non-singular. How? Because if it has unique perfect matching, then this H is unique. And this is a spanning linear subgraph whose components are edges only. There is no cycle component. That means this part is not there. So it is just a determinant is just a plus minus 1 if the graph has unique perfect matching. So graph determinant of a graph can be yeah.
So if it's non-bipartite graph,
it is for any graph.
You are saying that if a graph has unique perfect matching, then it is always non-singular. For non-bipartite graph, it is also true?
Yes, it is also true.
Okay. Okay, Dovinda.
Okay, thank you. So that's why we consider graphs with unique perfect matching, non-bipartite. So here in this talk, we consider graph, unicyclic graph, non-bipartite unicyclic graph with unique perfect matching. If we have unique perfect matching, then we have non-singularity. So we can talk about inverse of the adjacency matrix, and that way we can talk about inverse of graphs, etc. So once for non-singular graphs, because its adjacency matrix has inverse, so Harare and Ming, they have thought of inverse of a graph, and they have defined that a non-singular graph is invertible if its adjacency matrix is a matrix with entry 0 and 1. Because adjacency matrix of a graph is a 0-1 matrix, so they have just taken that simple idea that if its inverse is also a 0-1 matrix, then they call the graph is invertible. But this definition could not go far, because they have found that a connected graph is invertible if and only if it is just a P2. P2 means edge. So we just get a small class. So because of this reason, this Gottsil came up with some other notion of inverse of a graph. So what he defined, a graph is a non-singular graph is invertible if its inverse, if adjacency inverse of the adjacency matrix is signature similar to a non-negative matrix. Here S is a signature matrix. Signature matrix means diagonal matrix with diagonal entries plus minus 1. And he posed the problem of characterizing bipartite graphs, inverse of bipartite graphs with unique perfect matching. And since then, many work on bipartite case has been done. People talked about the people worked on inverse of bipartite. Lots of work has been done there, and I just list out few of them which will be which is required for our purpose. Then Barik, Neumann and Patti, they have given a combinatorial description of the inverse of the adjacency matrix of a bipartite graph with unique perfect matching. And then Agbori and Kirkland, they have characterized the bipartite unicyclic graphs having unique perfect matching which possesses inverse according to the Gottsil definition. And among those unicyclic graphs, Tiefenbach and Kirkland, they have identified those graphs which are self-inverse. Self-inverse means a graph which is isomorphic to its inverse graph. Then recently our Panda, Swarup Panda, he has supplied some characterization of bipartite unicyclic graphs with a unique perfect match which have bicyclic inverses. So keeping this in mind, we will go further. Now we give the definition of inverse of a graph the most natural way. We have a non-singular graph. We have the inverse of the adjacency matrix. Say it's ij entry is alpha ij. And by G plus, what we mean, the graph whose vertex set is just same as that of G, and two vertices I and J, they are adjacent in G plus if and only if alpha ij is non-zero. And we call that graph as inverse of G. And we will proceed with this definition of inverse. And before we proceed, we have some terminologies. So by Pij, what we mean, the set of all ij paths P such that G minus Vp has a spanning linear subgraph. For ij two vertices, any two vertices, by Pij we mean this. Ij paths is that G minus Vp has spanning linear subgraph. And we see that in case of a non-bipartite unicyclic graph with unique perfect matching, Pij can contain at the most one such path for any ij. Any two ij given any two ij, Pij can contain at the most one path. We have seen that. Now what is an MM alternating path? MM alternating path, that is in the literature, that is introduced by I think Swarup and others. So a path P is called alternating MM alternating path if it is an alternating path. That means its edges are alternately matching, non-matching edges, where the beginning edge is a matching edge and the last edge has to be a matching edge. That type of paths are called MM alternating path, matching. And with this terminologies, we have given a formula for the adjacency matrix of the inverse graph for non-bipartite unicyclic graph of order n with unique perfect matching. And this is the formula. So this formula suggests that the adjacency matrix of the inverse graph has the entries 0, plus minus 1 or plus minus 2. Because it is unicyclic, so we can have this 2 to the power something. So this 0, plus minus 1, plus minus 2. Whereas the adjacency matrix is just a 0, 1 matrix. And sometimes this alpha ii, the diagonal entries can also be non-zero. That is also a possibility. So we have to discard those things, those diagonal entries, non-zero things should be discarded in our next discussion. So because of that, as a consequence of that formula lemma, we can now talk about when two vertices are adjacent in the inverse graph. So two vertices I and j in the inverse u plus of u, they are adjacent if and only between I and j you have a MM alternating path. Now, before we proceed, we just talk about what is a mixed graph. Usually in the literature, mixed graph is a graph where we have two different types of edges, a directed edges and undirected edges. But as long as we are discussing the adjacency matrix of a mixed graph, this direction is not that significant for us. And that's why I just say mixed graph is a graph with two different types of edges, say red edges and say blue edges. And the adjacency matrix of the inverse graph is defined simply like this. The ijth entry is 1 if I and j adjacent and ij is a red edge, and minus 1 I and j adjacent, ij is a blue edge, otherwise it is 0. So the adjacency matrix of a mixed graph is a 0 plus minus 1 matrix. So now we are interested in characterizing those non-bipartite unicyclic graphs whose inverse graph is a mixed graph. That means the adjacency matrix of the inverse is just a plus minus 0 plus minus 1 matrix. We are interested in characterizing those type of non-bipartite unicyclic graphs. Now before we characterize, let us begin what is a peg. Let us have an idea what is a peg. So a peg is a matching edge. In case of a unicyclic graph, we are talking about pegs. Peg is a matching edge where one of its end vertex is on the cycle and the other end vertex is outside the cycle. So let us take an example. So this is a graph where red edges are matching edges, and that edge 4, 6, joining 4 and 6. This is a matching edge. One of its end vertex is on the cycle, the other is outside the cycle. It is a peg. Whereas this is not a peg because it is a matching edge, but both of the end vertices are on the cycle. Similarly, this is also not peg. So this theorem characterizes those non-bipartite unicyclic graphs with unique perfect matching whose inverse is a mixed graph. Now the inverse is a mixed graph if and only if U has at least 3 pegs. 3 pegs. Now it may be noted that in a non-bipartite unicyclic graph, you cannot have odd even number of pegs. You have to have odd number of pegs. And inverse is mixed graph if and only if you have at least 3 pegs. That means because of this theorem, this graph, inverse of this unicyclic graph cannot be a mixed graph because it has only 1 peg. We can see that. And this theorem gives us the entries of the adjacency matrix of the inverse graph U plus when the inverse is a mixed graph. This formula gives us the entries of the inverse graph, adjacency matrix of the inverse graph, and it is coming out to be in terms of length of alternating path between I and J. We can see easily, it can be seen that whenever there is an alternating path between two vertices I and J, you cannot have more than one. You have to have unique. In case of non-bipartite unicyclic graph with unique perfect matching, where U plus is a mixed graph. For those graphs, the adjacency matrix can be described by this. Okay. Now, the most natural question one can ask is, you are taking a non-bipartite unicyclic graph, you are considering discussing its inverse. So the natural question it comes to the mind is whether its inverse graph is also non-bipartite or can it be bipartite sometimes. So before answering that question, we have this lemma, and this lemma will answer that question. How? So this lemma says that whenever U has R pegs, then the inverse graph always contains a cycle of length R when R is greater than or equal to 3. And in particular, if R is equal to 1, that means if U has only one peg, then U plus contains a triangle. And you know that it can be seen easily in a non-bipartite unicyclic graph with unique perfect matching, you can have only odd number of pegs. You cannot have even number of pegs. And that means whatever be the case, if you have one peg, then you always have a triangle. If you have more than one peg, that means you must have at least 3 pegs, 3, 5, 7, and so on. So the graph has a cycle of length R. That means the graph always U plus, the inverse graph always have a odd cycle. So because of this lemma, we can say that the inverse graph is always non-bipartite. Whereas for the bipartite case, the inverse graph is bipartite. So non-bipartite case, we are getting inverse non-bipartite. So the inverse graph is non-bipartite. That is what we have seen. Fine. So then next question one can ask, to find those non-bipartite unicyclic graphs whose inverse is almost bipartite. Almost bipartite has some meaning. I will just explain what I mean by almost bipartite. Almost bipartite, just about to be bipartite, like that. So that is the question of quasi-bipartite. That type of graph we call quasi-bipartite. Not we call it, is people call it quasi-bipartite graph. Now what is a quasi-bipartite graph? So mixed graphs are usually called quasi-bipartite if we can partition the vertex set into two subsets, V1 and V2, such that the edges joining a vertex of V1 and a vertex of V2 are all red type of edges, and edges within V1 and V2 are all blue type of edges. That means the vertex set can be partitioned into two sets like this. So now this blue means any edge between edges of V1 is blue, any edge between edges between V2 is also blue, and any edge joining vertices of V1, vertices of a vertex of a V1 to a vertex of a V2 is red. So that is what quasi-bipartite graph means. So then we can ask the question that okay, inverse of non-bipartite unicyclic graph with unique perfect matching is non-bipartite. Is it true that the inverse graph of such graphs are always quasi-bipartite? So people ask that question. People means we ask that question, and we have seen an example. Let's take this example U1. And its inverse graph is calculated, and we see that this inverse graph is not quasi-bipartite. How? Suppose that it is quasi-bipartite, then we can partition the vertex set into two subsets, say V1, V2, such that edges within V1 are all blue, edges within V2 are all blue, and edges joining V1, V2 are all red. If we have that type of partition, and since there is an edge, a red edge between 1 and 6, then 1 and 6 has to be in different partite sets. They cannot be lying on same partite set. So say 1 is in V1 and 6 is in V2. But then this vertex 8 has to be either in V1 or in V2. Now if 8 is in V1, then because there is an edge between 8 and 6, that means you are getting an edge joining, a blue edge joining vertex of V1 to a vertex of V2, which is not possible. Similarly, if 8 is in V2, then also we are getting an edge between 1 and 8, where 1 is in V1, 8 is in V2. and it is a blue edge. So that is not possible. So that's why this graph is not quasi-bipartite. So then the natural question comes, then what are those U for which the inverse graph is quasi-bipartite? And what are those U whose inverse graph is not quasi-bipartite? And so this theorem tells us that answer. Suppose that U is a non-bipartite unicyclic graph with unique perfect matching, so that U plus is a mixed graph. Then its inverse is a quasi-bipartite if and only if the number of matching edges in the cycle has to be even. Otherwise, it is not quasi-bipartite. So this theorem tells us that answer. So these are all about structure of the. We are moving on about the structure of the inverse graph: bipartite, non-bipartite, and quasi-bipartiteness. Then, okay, the next question people ask for the bipartite case that inverse of a unicyclic graph, is it always unicyclic? Can it be bicyclic? People already answered those questions for bipartite case. So we ask those similar questions here. So we take this graph, unicyclic graph, and we compute its inverse graph, it's U plus, and they are just the same graph, almost they are same graph, just the labelings are different. That means they are isomorphic. So for this unicyclic graph, we are getting the isomorphic inverse. So one can say that this is a self-inverse unicyclic non-bipartite graph. So for bipartite case, people Tipping-Beck and Kirkland, they have proved that bipartite unicyclic graph they have characterized those bipartite unicyclic graphs for which the inverse is self-inverse. Then we see a different picture also. We take this unicyclic graph, its inverse is not unicyclic, bipartite, non-bipartite case, one is non-bipartite. The inverse is not unicyclic, but it is bicyclic. So we can ask those similar questions that where characterize those unicyclic graphs whose inverse is again unicyclic, and characterize those non-bipartite unicyclic graph, of course, because bipartite case bicyclic is proved by our Panda. Then for bipartite unicyclic having self-inverse that proved by Tipping-Beck and Kirkland. So non-bipartite case, we are asking that question, and we all more or less get similar kind of results. Now, before we answer that question, let us talk about what is a simple corona. So nowadays, all of us are scared of this corona, but we should not be worried about that corona, because this corona is not going to harm any of us. It will, in fact, help us. Now, what is a simple corona? So all of us, a simple corona is a graph which is obtained from another graph Z by adding a new pendant vertex, means degree 1 vertex to every vertex of the graph Z. So let us take an example. This is a graph G, and from Z we add to each vertex we add a degree 1 vertex, and the resulting graph, this graph is called a simple corona. So this theorem answers this question. It is similar theorem to the bipartite case. A graph U is non-bipartite unicyclic graph with unique perfect matching. So that U plus is a mixed graph, because U plus is a mixed graph is essential for us, because otherwise we may be having non-zero entry on the diagonals. Then the following are accurate. U plus is unicyclic, the inverse is unicyclic if and only if U is a simple corona, and if and only if U is isomorphic to its inverse graph. One can say self-inverse. So U plus is unicyclic, and it is isomorphic to its inverse, and it has to be simple corona graph. So then we have characterized the non-bipartite unicyclic graph with unique perfect matching. So that U plus is a mixed graph for which U plus is unique again unicyclic. So we have answered those questions. Then the next we want to characterize those non-bipartite unicyclic graphs whose inverse is bicyclic. And before we proceed, we construct two different classes of graphs. So how do we construct those graphs? So take an odd cycle of length n, and n is greater than or equal to 5. Then you would take n minus 2 simple corona trees. Simple corona trees means it is a corona, simple corona which is 3. So they are called simple corona. We take n minus 2 such simple coronas and choose a quasi-pendant vertex ui of ti for each from each of these simple corona trees. Quasi-pendant vertex means a vertex which is adjacent to a pendant vertex, means a vertex of degree 1. And attach this ti, this corona, simple corona trees at the vertex pi by identifying vi and ui. Vi is a vertex of gamma. So at the cycle, we are attaching n minus to each n minus 2 to n minus 2 vertices of that cycle. We are attaching n minus 2 simple corona trees. So here is an example that will explain everything. So we take a cycle of length 5 and we take a simple corona tree, say T1, and this red dot is to mean that it is a quasi-pendant vertex, and we attach it at this vertex. Similarly, we take another one, we attach at this vertex. We take another one, attach this vertex. And this is one example of a type F graph. Then we go to another class of graph which we call a type B graphs. So how do we construct this? So again we take an odd cycle, we have to take an odd cycle. And now its length can be 3, so it is greater than or equal to 3. And we take now n minus 1 simple corona trees. And from for each of these simple corona trees, we consider a quasi-pendant vertex, say ui in ti, and attach these corona simple corona trees at n minus 1 vertices of gamma by identifying a vertex vi of gamma and the quasi-pendant vertex ui of ti. Okay. So at the vertices of n minus 1 vertices of the cycle, we are attaching simple corona trees. Now, apart from this, now we take another two different corona trees, say T and T dash, and then X dash. And we pick a quasi-pendant vertex W of say T and W dash of T dash. And with the help of this W and W dash and this part, we are going to join T and T dash. How do we join? We just join the X WX and X dash W. So that will join T and T dash. And say that new tree obtained by joining T and T dash like this is a T naught. Now this T naught is not a simple corona. It is not a simple corona. We will see. Because this X, the vertex X, is a degree 1 vertex. And it is not adjacent to any pendant vertex. And finally, that T naught we attach at the vertex Vn left in gamma, because in gamma to this vertex Vn we have not attached anything. So finally, we attach that T naught at Vn by identifying a quasi-pendant vertex of T naught. Now, any quasi-pendant vertex T naught we take, we attach at Vn. Okay. So this is how we construct type B type of graphs. Just take an example. So we take this cycle of length say 5 And we take a simple corona tree. A red dot is a quasi-pendant vertex, and we attach it to this vertex of the cycle. Then we attach another simple corona tree here. Then we attach another. So we will attach 4 corona trees like this. And now we take two different corona trees, T and T dash, and a path. Path means just an edge. And we join, and this dot, red dot, again quasi-pendant vertex. We add those edges. Now this is a tree. Now this is not a corona tree because to this vertex you do not have any other degree 1 vertex adjacent. Now we take this. This is your T naught. This is your T naught, and we attach this at this vertex of the cycle. And this is a graph of type B. And what we prove is the following: that a non-bipartite unicyclic graph with unique perfect matching, whose inverse graph is a mixed graph, and the inverse is always bicyclic, if and only if the graph U is of the type A, that's just now we have described, or it should be of type B. That means these type of graphs are only graphs whose inverse is bicyclic. That is what we have proved, and it is a more or less similar kind of results that proved by our this for bipartite case. This Panda proved characterized this inverse characterize those unicyclic graphs whose inverse is bicyclic. So with this structures we so far what we have described the structure of structure of the inverse graphs, the bipartiteness, quasi-bipartiteness, unicyclic, and then bicyclic. And we have found some tricyclic case also, but we are not going to discuss in this talk about those. And I, along with my student, we are working in this direction. In this is a small step towards the non-bipartite case. We have worked few things here, and with this we stop this talk. And these are some references. And thank you all.
Thank you, Debajit, for the interesting talk. Yeah, audience, if you have question, can ask. Okay, if there is no other question, let us thank Debajit. And thank you. So, Debajit, please send the slides to me. I will circulate to the participants if it is all right.
Okay.
Yeah. So I have recorded the video. I will forward the videos to everyone.
Okay.
Yeah, I think there is a question in the chat box.
Okay.
Can you see?
Yeah, let me see.
Yeah.
We have defined it with 2 colors, and we define with 3 colors. Yeah, that is there in the that is there. This is we have worked something like that. 3 colors. 3 colors. It's 3 different types of edges, one can say. That type of things are there in the literature. So we have worked on those type of things.
Okay, so means like for one color, say blue, you have put 1. For red, you have put -1. Say if we have another color green, so means what possible value we can
That
take?
is we have defined it to be plus minus I.
Oh, okay.
Yeah, in fact, there are more generalized things are there in the literature.
Okay.
One can think about this gain graph, unique gain graph. Those also can be thought of this type of coloring different types of graphs, just you can say. In that case, directions will matter actually. Yeah. In that case, for mixed graphs, directions does not matter, because as long as you are having this 1 and minus 1, direction does not matter, because adjacency matrix remains same, whatever direction it is. But in case of say if you take gain graph, then the direction matters. It will change. It will change the direction. The adjacency matrix changes. The Laplacian matrix changes.
Right. Okay. Thank you, sir.
Okay.
And also, sir, one question I want to ask, like your work is related to singular and non-singular graphs. So, any work has been done related to distance matrix, means what all are the characterization of those graphs for whose distance matrix is non-singular?
Yeah, there are works on this type of thing, about distance matrix. There are works, but I have not studied those distance things. But there are works as far as I know.
Okay, sir. Okay.
Okay, if there is no other question, let us thank Debajit again. Yeah, thank you, Debajit.
Thank you. Thank you.
Thank you. Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Okay.
Debajit,
Yeah.
that Sharma you told, that is Baba Kumar Sharma? Just sorry.